Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button, and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. My guest is Dr. Rebecca Larson. She's at the Rochester Institute of Technology as a postdoc. She recently got her PhD at University of Texas. So we're going to talk about the James Webb Space Telescope and how it's reshaping astronomy. So welcome, Rebecca. Thanks for coming.
Thanks for having me.
If you would, tell me a bit about your background and how you got to work with the James Webb Telescope results.
Yeah, sure. So I didn't have a very traditional path to astronomy. I enlisted in the military out of high school. I was an Arabic translator, taking as much college as I could and trying to get my education. When I got out of the military, I went to school full time, originally for business and art, but then transferred to the University of Texas and had to pick a new major by an alphabetical list. And I thought, I don't know, I like sci-fi and space is pretty cool. So astronomy, I guess. And I ended up completely falling in love with the research aspect of it and really enjoying the science. And so I applied to go to graduate school to get my PhD, which I just finished this year at UT Austin as well. And I've been very fortunate to study galaxies early on in the universe, and which is one of the main motivations for building JWST, but also one of the really cool new discoveries that we can make in the astronomical field is studying galaxies that were more distant than we could see before. So galaxies earlier on in the universe and also ones that are fainter. And so this was kind of the telescope that we needed in my specific field of astronomy. And it's very exciting to get to be some of the first people that got data on it and working on that data and learning about the early universe, right out the door is pretty cool.
Are the images available to everybody, or only the person that proposed that particular experiment's allowed to look at the images from it?
Yeah, so that's a great question, especially in today's world of kind of open science and public data. With JWST, there were a lot of programs that were approved prior to the telescope even launching into space, and some of those programs were called early release science programs. Those programs were meant to test capabilities of the telescope, and in exchange, we were some of the first teams to get data, but that data was immediately public and available to anyone, not just those of us who proposed for it. There are different programs that have proprietary time. So those data are only visible to those who proposed for it for up to 12 months. But there are large programs. There are different kinds of observing programs that have been proposed that were immediately released to the public. So anyone who is interested really can kind of download the data from the archive and take a look at it and like as soon as we do as well. So
yeah, but it hasn't even been around for a year, right? How is there data that you're waiting on that's not available yet?
Yeah. So the telescope started taking data for science purposes about last June of 2022. The first data release was with the image releases that NASA did in July. So mid-July was when the data actually finally was no longer embargoed and was released to the scientists and, well, some of the images to the public as well. And so it has been a year since the first data release. So anything that was taken then and was not public immediately already is. But the telescope is taking data every single day. And so it kind of staggers. So if something is taken today with a proprietary period, it has a year, then we won't be able to access that unless we were on that proposal until, next October or so. But the data that was taken in the first year, so to speak, is starting to become public as we go through. And right now is an interesting time to be talking about this because we're in the middle of the third cycle of proposal call. So we're proposing for time on the telescope. This is a third call for proposals, and those are all due in like 3 days, 5 days. I don't know, but time it is. And those will be for observations that start, next July. And so it kind of just keeps going in kind of incremental yearly cycles of proposals and observations.
Right. But what data is available that you have looked at that has been useful to you and why?
Yeah. So personally, I've been focusing predominantly on a program called the Cosmic Evolution Early Release Science Program, or CEERS, CEERS. And that data was public immediately once it was taken. We had data that was taken in July or June and released in July of last year. And then the second half of our data was taken in December of last year. We had a few that were kind of the telescope did something strange and so got retaken again in February. And then we had some other data taken in March. And so all of these data sets were public immediately. So they were available to everyone at the time. In my particular case, we have imaging. So images of this, what would look like to your own eyes, a blank spot in the sky that has thousands and thousands and thousands of galaxies in it. When we get the images with JWST, we've released a public image for anyone to take a look at. That is a color image where we've taken all of the different wavelengths that we've observed, put them into different colors, and then combined them so it's a color image of this field of galaxies, which you can find if you'd like to look it up. It's the CEERS field, again, CEERS. NASA did a press release a couple months ago with the full color image of our survey field. And if you have a computer, please don't download it on your phone. The file is really large. You can download the image and you can look through it and just keep zooming in because there are so many galaxies. And if you just keep going and zooming in, and there's more and more things for you to find, and you can definitely get lost in that space with us. These images are of a field, a spot on the sky that we've studied extensively with the Hubble Space Telescope and many other telescopes prior to JWST. And so we had specific things that we were targeting, that we really wanted to look at this particular galaxy or that particular galaxy because we knew about them already. And one of the science cases for our program was to look at some of these galaxies that were very early on in the universe, which we had discovered with Hubble. I spent many years on one of the largest observatories on the ground, the Keck Observatory, trying to obtain spectra or very discrete data from these galaxies to measure their distances very accurately and understand their properties. And so some of the sources that we were observing with this program, we got images of, but we also got spectra. And so with those spectra, we're able to actually see the different elements that existed in these galaxies and how abundant one is versus another. We're able to see kind of from that, the elements that are there, that we can determine what kinds of stars existed. We can understand a lot about the actual processes that are physically happening inside these galaxies that existed over 13 billion years ago. And in my particular case, one of my recent discoveries and what I've used JWST to find was a very distant, and at the time most distant, active black hole at the center of this galaxy based on the spectra we got with JWST. And so that, I think, was also another NASA press release that came out over the summer talking about how we find these distant galaxies. And that's what I've particularly used this telescope for is true.
So what are you seeing with faraway stars that weren't observable before? What's different about them? What's interesting that you're observing?
Yeah, so there's a phenomenon called redshift, which is because as light left galaxies in the early universe, 13, plus billion years ago, that light was traveling through space and time as this space and time itself was expanding. So our universe is expanding and the light is actually getting stretched out to longer and longer wavelengths. It is shifting to longer or redder wavelengths. And so astronomers have called this redshift. What that means is that if you have ultraviolet light that left a galaxy 13 plus billion years ago, over those 13 billion years that the light has been traveling to us, to our telescope, that it has stretched all the way through the ultraviolet, through the optical spectrum and into the infrared. And the infrared is what we really needed to study these galaxies, because ultraviolet light is where, bright young stars emit light at those wavelengths. They're incredibly bright. A lot of what Hubble has done in these very beautiful images we see are ultraviolet or optical light from galaxies that are nearby. But in order for us to see those distant galaxies in the same way, we have to look in the infrared due to this redshift. Now, we could only see so far into the infrared with the telescopes that we had prior to JWST. Hubble was able to do this to a certain point. We needed a higher resolution detector and we needed a bigger telescope to see fainter things at higher resolution at these wavelengths. And we needed to get it out of the atmosphere because the atmosphere also blocks infrared light. And so we could not see these stars. We could not see these parts of galaxies prior to JWST due to the fact that we just could not observe those wavelengths in enough sensitivity and detail to see these galaxies prior to having this particular telescope. But what we're also finding is that we had some theoretical models of what kinds of stars and how many these early galaxies had and how big their black holes needed to be and how much how many stars they formed on average every year. And I think what we're finding with JWST now that we actually can observe these galaxies is that there's far more brighter sources. They are far more active than we expected, which is fun because, when it's something unexpected, that's when science gets really interesting. But it's also great because some of the first things that we're going to find are going to be the brighter things, the easier to see objects. And so that's meant the first year of discoveries with JWST were incredible. I think we were all very pleasantly surprised. Not only is the telescope much more sensitive and much better than our best predictions, but these sources are actually brighter and we're able to see them with less observing time we thought we would need to spend.
But what is this telling you? How does this change the picture we have of, let's say, the early universe or distant stars?
Yeah, so I think what's interesting to me about this whole kind of experience and endeavor is that we had some assumptions about galaxies, about how they form stars, how many stars you would make out of how much material. And we used all of the data we had from nearby galaxies to inform us based on these understandings. And I think what we did is we projected those understandings of galaxies that exist in today's universe to galaxies that existed in the early universe. And I don't think that we accurately accounted for how different the universe was itself in the early times and how different these galaxies were. And we didn't have a way really to see them to begin with, so that we couldn't, kind of hone in on the right properties for our models. But I think what we did is we naively took our own universe view and applied it to galaxies that lived in a very different environment than the ones that we see today. And so we are learning how better to recalibrate our expectations and to account for the fact that galaxies early on didn't have enough generations of stars to explode into supernova and then fuse heavier elements. So they just didn't start with as much, dust that, we have in our galaxies today. We also see stars in the early universe that are larger, based on the fact that if you have this much light in a star that doesn't have heavier elements, it's just hydrogen and helium, and the lighter elements, then you have a larger star for the amount of light it emits. And so when we do a lot of conversions from this is how much light there is to how much, what that would equate to as mass, like how massive is this galaxy? Those conversions were incorrect because they were calibrated to galaxies that had stars that were made up of different elements. And so I think that's the fun part about this, is that we needed to rethink how we were thinking about galaxies in the early universe and not apply our own biases to these galaxies that were fundamentally different, and the universe was much smaller.
So what does that mean? So that the formation of heavier elements took longer than people thought? Or, I don't know. What's the implications of this?
No, I don't think that there's any, honestly, personally, I don't think that there's any, fundamentally incorrect assumption we had about the universe. But I think the way that we typically measure physical properties from the light of galaxies, those equations that we use, we were not calibrating them properly. I don't think that we've found something incredibly surprising or breaking what we expected, other than, I don't think our expectations were correct. So I think what's interesting about JWST is before this telescope, before we had this data, there were maybe a handful, but less than 10 sources, galaxies that we knew about for sure that existed in this time. We couldn't really study them in a whole lot of detail. We just didn't have the technology. I mean, within the first few months, we're looking at hundreds of galaxies. And over the last year, we have more galaxies than I can even remember. I'm so used to just knowing what those 10 sources were, those 10 galaxies are. And now we've got so much data that we are putting into context a lot of the sources we knew about are going to be the rarer ones, right? They were brighter. That's why we were able to see them before. But now we want to understand, like, are they normal? Is that common for galaxies in the early universe to have those particular properties, or are those galaxies, the rare, unique ones? I mean, we have a lot more data to do something statistically significant with, and we're still trying to, go through all of it. It's a lot of information and trying to put a lot of things into context while also being aware of our own biases in our understanding and interpretation, but also in the observations, right? The first year we pointed at all the stuff we knew about already. That was the most logical thing to do. But is there some bias in looking at the things that we saw before? Those were bright sources. So I think what we're going to see in the next year is a lot of data that is of galaxies we just had no idea existed before. We couldn't see them, and we'll be able to understand in a larger sense what the early universe was like, what those galaxies were like in general, and not in unique, rare cases.
What particular questions are you trying to ask or answer with your proposed, visualizations from James Webb and from existing ones that you're looking over?
Yeah, so I think what we really want to understand is how different were these sources? Did they form stars faster? Were they more efficient with their material and converting it into stars? How did the black holes, the supermassive black holes at the center of these galaxies, how did they grow? What did they form out of? How fast did they grow in a galaxy that's also growing? How often did galaxies merge? And what was the impact on those mergers in their growth? Right? Did they merge and then, kind of two and two add together, or did that disrupt the process and kind of break them apart? I think there's a lot of really interesting questions about how galaxies grew from very early, and their black holes grew into the ones that we were able to observe in much more detail prior to JWST. So the first, several 100 million years after the Big Bang are interesting. We only had theory to explain how we got to the galaxies that we saw at about 1 billion years. And now I think we want to understand the processes that these galaxies underwent in order to grow into the ones that we see, after 1 billion years, but also, again, after 13 billion years. Like, how did we get to the galaxies we are in now? And can that inform on a lot of fundamental processes about stars forming and how gas and dust interacted in galaxies, especially when, there are a lot potentially less complicated, but maybe more chaotic systems than the galaxies that we see, today, the big spiral galaxies like our own.
Well, how far into space, or how far back in time can we look now with James Webb versus before? And can we do a view of looking at the same part of space and then kind of stepping forward in time all the way to present? Is it possible to get that kind of a view over the same patch of sky?
Yeah, so those are interesting things to consider. So for your first question about how far back prior to JWST we could see, I think the most distant one was a little under 500 million years after the Big Bang. And now I think we're getting down to the 300 million years after the Big Bang for certain. There's some that are, we have imaging and we think that these galaxies are at this distance, but we need spectra to confirm it and things like that. So I think some of the most distant galaxies, we're getting into the 300 million years after the Big Bang range right now, but also really truly fleshing out a whole sample of sources from, 300 million years to a billion, which, like I said prior, we had one, but we had maybe, a handful that were in the 600 million year range after the Big Bang. And now I think we have more than I can count or can keep track of at the moment. And to your second point, we cannot see the same galaxy or set of galaxies from like their early times until today. We can stare at that same spot in the sky, but basically we're seeing snapshots in time. And it's not going to be those same galaxies that we see early on that we're seeing later. The universe has expanded and those galaxies are actually in a, maybe they don't exist anymore, but also they are in a different place on the sky as they've expanded kind of out of that particular spot. But what we can do is we can get a lot of images of galaxies at different snapshots in time and try to put together a lot of, if we just have...
Well, what if you look in the same spot at reduced depths of field and take successive images? What would it look like?
So you would see galaxies at different distances, but they are not the same galaxy. They will be different galaxies. And so you can, and this is what we do, we take an image of a certain spot on the sky and you'll see larger galaxies which are nearby and smaller ones which are going to be fainter. And so what we have done, if it's interesting and maybe helpful in answering your question, is we have done kind of a fly-through video where we take, our big Sears image in today's world and then kind of fly through in time and space, and every second going back something like 200 million years or something like that, all the way back to one of the more distant galaxies we found at the very beginning called Maisie's galaxy. So it's another, video I think if you're interested, you should definitely look up. It's a fly through. It's from NASA. It's of the Sears field. And that can kind of show you what we're seeing about galaxies that are closer. And then as you get further and further away, they kind of look little and blobby and there's like less of them and stuff like that. If we are taking images at different depths in the same spot, we are not seeing the same galaxies, but we are seeing galaxies from different times in the universe's history, the further and further back we go.
Yeah, well, why not, again, look at a particular point and maybe do, 10 visualizations in a circle around it, spaced so that the field of vision just about overlap. What would you see pass through that set of circular views around a point over time? You might be able to capture that galaxy moving out in one direction or another. Would that be possible?
I don't think it would work in the way that you're thinking, and it's kind of hard to explain without a visual, but also effectively there's stuff in the way, right? So imagine you have a galaxy and it's in a specific spot and perhaps the universe and space and time is expanding. So literally everything is getting further and further away from each other. But there's also galaxies that are now moving in between us and that original galaxy. So if you're taking an image at a specific place, you can't see what's behind the thing that's blocking your field of view. And this is happening kind of everywhere. So it's not like I can take a picture of a specific thing over time because that light left that galaxy, let's say 2 billion years ago. And then as the galaxy moved, maybe we saw light coming from it 1 billion years ago, but we can't take a specific snapshot because the light is reaching us at the same time. And so they're going to be in different places, but the light has traveled different amounts of time to get to us. And that galaxy isn't going to look the same after 1 billion years as it did when we first saw it. So I don't think that we can specifically tag a galaxy and say, I see this here, and it's the same galaxy over here. Your viewing angle is going to be different. The size is going to be different. The way it appears and what it's gone through over the time since you've seen it have changed it quite a bit. We can do this in things that are much closer to us, like in our own Milky Way. We can kind of see where stars formed from, and there's a really cool field of galactic archaeology, which is kind of tracing back where the stars originated from based on what they're made out of. So you could kind of tag a star and understand its chemical composition and understand what cloud it formed from and other stars that have those same properties. But we can't do that on a galactic scale.
But what if you made like a cylinder that was your vision? The cylinder had, I don't know, 12 observation points within it. I don't know how big the field of view is, but just make something up. And then you tried to look, what do you see at all those points? When the universe was, let's say, 1 billion years old, that depth of field, and then you slowly raster it in or ratchet it in and look at the same 12 points in the cylinder view, just keep ratcheting it in closer and closer and closer. I'm sure some spots will be obscured, some not. But has anyone done that? Would that even be a useful way to look at a patch of the universe?
I mean, we do this all the time, right? We go back and observe the same spot on the sky to get deeper images and things like that. But you have to think about the amount of time it takes for the light from that source to reach you. It's not going to be 3 days. It's not going to be 5 years. It's not going to be 10 years, right? If you were to take an image and then, like you said, take another one at different depths, the amount of time between those images is nothing. That galaxy has not moved in 10 years. That galaxy has moved in 100 million years, but we don't have pictures from this specific spot in 100 million year time frames or 10 million years. Our lifetimes are so short. The way that we're seeing the universe is kind of in a stable place, unless, again, it's something in our own galaxy or the planets that are moving on timescales that we can perceive. You're thinking about it in a way that does make sense, except for the fact that the time between those images would have to be millions of years, not 2.
But what would be a sensible distance and jump? Let's say I'm looking out, 1 million light years, and I raster into, 500,000 light years, and then 1/10 of a million. I do bigger jumps. And again, look at kind of the same area, just different depth of field. Is there a way to get anything useful?
You'd have to, to get what you're asking for, you'd have to do those in that time frame as well. You couldn't do them, right? It's about the amount of time, right? So we can do this, the stars that surround Sagittarius A star, the black hole at the center of the Milky Way, we can take pictures of them over time and they're moving such that we can see them move, just like we see planets orbiting other stars. Galaxies, are very, very far away. And some of these are billions of light years away. And so we would not see them move on any kind of time frame that we've even existed in the way that you're thinking. It's kind of a complicated, it's a complication in how we would have to study the universe. But in order to overcome...
Well, don't we see... Okay, so if I'm looking at an object that's not very distant, wouldn't I be not only seeing the light from it that's recent, but also all the other light that is at various ages that has caught up to the same depth of field?
No.
You wouldn't see that? Why?
No. I mean, what you would see is basically like a snapshot in time, but in multiple different times for that specific spot. And like I said, it would not be light catching up because that light takes time to travel. And so for you to see something over multiple stages or light from the same source coming at you, that source would have had to have been stationary for that period of time in your field of view. And nothing is. The universe itself is expanding. So the space in between sources is expanding. And so if you were to look at one specific spot, you would have to look at different places to see those same things at different times, because they are not physically, that space that they physically existed in is no longer there.
Right, but is space expanding faster than light travels or slower?
Early on in the universe, right after the Big Bang, it expanded faster than the speed of light, but since then, no, it has not.
I would just think there would be, again, some overlap. If I'm looking, let's say, at the moon, and then 2 stars that are kind of in the same field of view, and one star is 5 light years away, one's like 1 million light years away. Their light, again, so their light wouldn't change what I see from looking at the moon, let's say, in the moon's field of view.
Yeah, I mean, stars are on a scale. Those stars are stars in our own galaxy. Those are things that, yes, we can do that for. But if you're talking about galaxies are too far away in time and space for us to do something like that.
Okay. Is there any difference in viewing something that's so far away, it's so early that, again, it was expanding faster than light versus nearer field stuff that was expanding slower than the speed of light? Is there a discontinuity when you view out to a certain depth or a certain amount of years back in time? Are there jumps in what's observed, or like discontinuities in what's observed?
Not that I'm aware of. Now, I did say that, the universe expanded faster than the speed of light right after the Big Bang, but that was for a fraction of a fraction of a fraction of a second. And so that's not something that we can observe in the way that you're thinking. And so that we would not see kind of a disjoint between that, which we cannot observe, and then what we can observe in the early universe. There is something that we can see change in galaxies, and we've seen this with JWST. We've observed some of these galaxies with Hubble, maybe 10 years ago, 5 years ago or something. We observed them with JWST, and we can see a supernova has gone off. And so you can kind of convert the amount of time it's been here versus the amount of time it would have to be there. And what we do see is that is a time scale, right? That we can see a change in the same source. And we've found, I think within the first few days, there was a supernova that was found in the Sears images. And then there's been several more that have been found in the clusters that we've taken images of. You can see supernova, like big bright spots in specific galaxies that were not there the last time we observed them. And so that's been a pretty cool kind of thing to catch. These are much more distant. These are supernova in other galaxies, not in our own, not in nearby galaxies. These are very far away. And we just happen to kind of observe in a long enough kind of time frame between Hubble or JWST that we're able to see the supernova go off. And I'm sure if we observe them again in 10 years or so, that supernova will have turned off from our perspective.
Has the expansion rate of the universe continually slowed down, or was it faster and then it just settled to a certain constant rate and has maintained that rate?
Yeah, so that's an interesting question that a cosmologist would be better able to explain. But from our understanding, the universe is expanding and it was at a pretty constant rate. But recently, in cosmic time, that expansion rate has sped up. It's accelerated. So the universe is now expanding at an accelerated rate than it was. And again, I don't think this would be noticeable on the time scale of like our observations like we've been talking about, but this is something that is still unknown. There's got to be some amount of energy being put into the universe on a whole scale in order to accelerate that expansion. And this is what we've called dark energy. And so trying to understand what is speeding up or accelerating the expansion of the universe is a big field of study. And a lot of cosmologists are looking into doing this. And we can observe galaxies at different times across large areas of the sky and try to measure how their distances change based on a couple different techniques. There's a really cool survey called the Hobby-Eberly Telescope Dark Energy Experiment, or HETDEX, which is being done on the McDonald Observatory that is owned by UT out in West Texas. And so I encourage you to kind of look into that for some of the early results. That data is still kind of being taken, but trying to measure the distances to a lot of galaxies and see if we could see any kind of fluctuations in those distances, which is again not something I'm an expert in per se, but it is an ongoing field of study in astronomy that I encourage you to look into if you find that interesting.
Well, when you said that the expansion rate has sped up, quote unquote, recently, like when would that be? What's the bookmarks of the time frame in which it may have sped up? I
don't want to quote an actual number because I don't know what it be in years, but if it's relatively recent, and in the 13.8 billion years of the universe is within the last one.
Is it related at all to density? Like, is the expansion happening the same in all spots? And if you look at the early universe, it would have been, I guess, a lot more dense than now. So is that why it expanded more rapidly in the very beginning? Or, again, is the expansion rate correlated with density of objects in the universe? That's
a great question. I don't think that the expansion rate correlates with like more dense areas would be expanding faster. Everything, the universe itself, all of space and time are expanding at one rate or another, right? So it's not based on where like matter in the universe is, that as far as we know, right? And so it's kind of happening everywhere all at once. And early on in the universe, right, like when we talk about how it accelerated incredibly fast, it was after the Big Bang, right? Everything kind of spread out everywhere really, really fast, faster than the speed of light. And then the densities, the different density like fluctuations basically of matter in the universe was when stuff started to form. Stars started to form, molecules started to form, all of that. And more dense areas had more, mass or matter or elements to start forming things. And that's where the first stars and galaxies started to form, or more denser areas. So the matter itself is tied to the density, but the expansion itself does not seem to correlate to any of that. It's a universal kind of experience.
All right, well, very good. So what's the best way for people to find out more about your work and to keep tabs on, hopefully your project that gets funded with or gets timed with the James Webb Telescope?
Yeah, I knock on wood. Yeah, so personally, my website, I suppose, if I remember to keep it updated, is saturnswings.com, and I think my handle on all of the social medias is saturnswings as well. But particularly for some of the really cool JWST results, I'm biased, right? I'm excited about my own science, but there's a ton of really cool research that's being done worldwide with this telescope in totally different fields of astronomy. And so if you're interested, there is a website that NASA has of a lot of their press releases and the new results that are coming out, some of the pretty images if you would like to download those. So I recommend going to, I want to say it's webtelescope.org, but I can't be certain if that's where all of that content is, but you can find it at NASA's website. The European Space Agency also does a lot of the releases of the science that we're doing. And so ESA is also a good place to take a look. It's a partner between NASA, ESA, and the Canadian Space Agency, and a lot of other places around the world that the scientific discoveries are coming out of. And so hopefully if it's something you're interested in, and I highly encourage you to take a look at some of the really cool images we're getting at the very least, those are great places to go. Our particular program, the SEERS program, is at seers.github.io. That's our website, and you can find out a lot of information about our particular program. But I again encourage you not to just look at our stuff, but a lot of the other really cool science is being done.
Okay, very good. Well, Rebecca, thanks so much for coming on the podcast. I really appreciate it.
Thanks for having me. It's been great.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.